let's come up with a power series form of this given sequence of numbers following the idea of the exponential generating function. Again, we are going to express this into an exponential generating function of the original form. Say, for example, if we have here terms a sub 0, a sub 1, a sub 2, until a sub r in our sequence and so on and so forth, we can actually write this as a function, exponential generating function specifically. You have your a sub 0 plus a sub 1 x over 1 factorial, that's factorial, plus a sub 2 x squared over 2 factorial, plus a sub 3, you have x cubed over 3 factorial, until we reach here a sub x to the power of r over r factorial, and so on and so forth. So looking back here, we can have this form here. For this, let's start with the form first of the function. So we have our a sub 0 is 1, and a sub 1 is k times x over 1 factorial. And then you have here plus a sub 2 as x, or our a sub 2 rather, let's substitute that, k squared, x squared over 2 factorial, plus the third one is k cubed, then x cubed over 3 factorial, until you reach here k to the power of r, x to the power of r over r factorial, and so on and so forth. Now, for this consideration, we can actually look into the relationship of the numerators of each term. That's actually 1, plus you have kx over 1 factorial, plus you have here k squared, x squared over 2 factorial, plus you will have here k cubed over, and x times x here rather, over 3 factorial. Then you have here plus dot until you will have k to the power of r, x to the power of r over r factorial. This is the form for the exponential generating function of the given sequence. Now our next task is to come up with a certain power series for this. So I would like you to take your attention to the given identity we had previously identified in one of the videos in this playlist. You might try to review that. We actually have this form f of x, or let's try to use another function, let's say g of x. Before, we have 1 plus x over 1 factorial plus x squared over 2 factorial, okay, and then we have here plus dot until x to the power of r rather over r factorial can be written as a power series in this manner. You have x to the power of r over r factorial, this term, that term, for r starts from 0 to positive infinity. It even has an equivalent form of e to the power of x. Again, indication of this is an exponential generating function. Now, let's try to look into their relationship. When we talk about here, we will say let me use the white one. Let kx be another, the kx, we also have kx here. So let us try to do it first. Let me bring you to this portion. You have 1 plus kx over 1 factorial. What if I'm going to apply the power law here, the reverse? So this is actually equivalent to kx raised to 2. By power law, it returns to k squared x squared over 2 factorial. Plus, this is also kx power of 3 over 3 factorial. Plus, until here, it's actually just equal to kx to the power of r over r factorial. When you look at this two, this is now similar, as we will have an expression raised to the power of r, expression raised to the power of r divided by r factorial. Similar here, kx squared as 1, so you have x squared over 2 factorial. What's my point here? What if I'm going to denote it like this? Say, for example, I'm going to let here, okay, let kx be equal to any variable, let's just say y, just for this instance, because I would like to produce a a power series for this that will be using this concept in probably a form of exponentiation. Okay, so if y is equal to kx is equal to y, so the next form here, pardon if this no longer be equal to f of x, don't worry, we will return to that later, but just for this, we have 1 plus y over 1 factorial plus y squared over 2 factorial. Okay, the kx itself is y, so cube over 3 factorial until you reach here y to the power of r over r factorial. I'm letting that one again because when you look at these two, they are now similar in form. One, you have x over 1 factorial, or in this case y, x squared, y squared, and so on and so forth. In short, we can write this into a power series in this form, but instead of x, we'll be using y. So you have the summation of y to the power of r over r factorial as r starts from 0 to positive infinity. But since we had already earlier as y being kx, by substitution, you will have here kx raised to r over r factorial as r starts from 0 to positive infinity. So this is the equivalent power series of our given item here, our given sequence, or you can even write this as distributing the exponent r. So you have k to the power of r, x to the power of r over r factorial as r starts from 0 to positive infinity. They are just the same as we distribute that using power law. If you would like to have an expression like this, basically, if we talk about this form earlier, or this form, let's have this one. We have summation of y to the power of r over r factorial as r starts from 0 to positive infinity. So you will have here this similar. This is actually equal to e to the power of y, where then again y is kx, so this is actually equal to e to the power of kx. This is the exponentiation form of this power series, which is also equivalent to the given sequence of numbers here. So when you see something like this later on, say for example, if you're asked, I'm going to give you a hint here. Say for example, you're asked to give the sequence for e to the power of 2x. That means your k is equal to 2, right? So our sequence earlier was 1, okay? 1 k, k squared, k cubed, so on and so forth. So with k is equal to 2, this is actually equivalent to the sequence 1, 2, 4, 8, and so on and so forth. Okay? So basically, that's an example for that. Okay? Anyway, this is the result for this item. Thank you very much for watching.